Welcome to this explainer. Today we're diving into something truly mind-boggling. We're going to look at exactly how a single human hand can hold back 150 tons of steel suspended 2 miles deep in the earth. If you've ever wondered how these massive industrial rigs handle, astronomical weights without just instantly tearing themselves apart, well, you are definitely in the right place. Picture this. An astronomical 300,000 pounds hanging right over an open hole. To put that into perspective, that's roughly the weight of a commercial airliner, just dangling there. And the only thing preventing that immense weight from crashing down and causing a very, very expensive disaster is a man's right hand resting lightly on a lever. Now, what's really fascinating here is that the man isn't strong, but the lever is. Understanding how one hand can effortlessly control 150 tons is literally the key to understanding the entire hoisting system on a mega machine. It's really not about raw power at all. It's all about incredibly smart mechanical design. All right, Section 1. 2 brakes, 2 jobs, division of labor. So looking at the Drawworks, which is essentially the massive winch on the rig floor, it actually relies on 2 completely different brakes, and they have entirely separate jobs.
The system is divided by function. The main friction brake, its only job is to clamp the drum to a dead stop and park the load. That's it, stopping and holding. Then you've got the auxiliary brake. This uses either electric eddy currents or fluid hydromatics. And here's the kicker. This brake doesn't hold anything. Instead, it continuously absorbs energy to control the descent as the load runs down, turning all that motion into heat that's safely carried away by water.
A great way to picture this is the mountain truck descent. Think of an experienced truck driver going down a steep mountain pass, right? They're going to use the engine brake or the retarder for the whole trip down to keep their speed in check, and they save the actual foot brake purely for the corners and that final stop. The Drawworks auxiliary brake is exactly like that engine brake. If you try to ride the friction brake all the way down, well, it's going to end in catastrophe. Which brings us to Section 2, the physics of heat, millions of foot-pounds. Because when you're lowering thousands of pounds of pipe 100 times a shift, the energy calculations become, well, truly staggering. Let's actually run the numbers. Energy equals weight times distance. So if you lower that 300,000-pound load just the length of a single 90-foot stand of pipe, you are generating 27 million foot-pounds of energy. And that energy doesn't just vanish into thin air, right? It has to become heat somewhere. If you try to absorb that on friction surfaces 100 times a shift, you're pumping literal industrial furnace levels of heat into those steel bands. That is exactly why the auxiliary brake handles the routine work, so the name brake stays cool for the exact moment you actually need it. Okay, let's test your active learning here. If the auxiliary brake is so amazing at absorbing all that energy and doing the heavy lifting to slow the pipe down, why can't a driller just use it to hold the load when the block is parked? Take a second and think about that.
The answer? It's because its resistance relies entirely on motion. An eddy current or hydromatic brake generates its braking force from the drum actually turning, which means, at 0 speed, it provides absolutely 0 holding force. It slows you down beautifully, but only the friction brake can physically lock a stationary load in place. You can never, ever park a load on the auxiliary.
So, the crucial takeaway here is that if you ignored this and just rode the main friction brake the whole way down, you'd induce a terrifying failure mode known as brake fade. This is where those incredibly hot bands silently lose their grip. And the truly horrifying part is, fade doesn't announce itself. To the driller, the lever feels exactly the same in their hand, but the load just keeps moving. Basically, the harder you've been working the brake, the less it grips when you absolutely need it most. Moving on to Section 3. The capstan effect, exponential force. Let's zoom in from the macro system down to the microphysics of the brake band itself. We really need to see exactly how a simple lever, pulled by a human arm, holds back a literal mountain of weight without snapping. It all comes down to what I think is the most elegant piece of physics on the entire rig, the capstan effect. So the flexible steel strap wrapping around the drum uses friction along that wrap to continuously add to the tension. Because of this, the tension doesn't just grow steadily, it grows exponentially. You pull one end with 100 pounds of force, and thanks to the friction wrapping around the drum, the anchored end can safely hold thousands of pounds. A perfect analogy for this is a rock climber's belay. When a climber falls, the belayer isn't catching them with raw muscle, right? A single hand can effortlessly hold a falling person's entire body weight, purely through the rope's friction running over a metal device. The Drawworks brake relies on the exact same physics, just scaled way up to 150 tons.
The band amplifies the driller's force. It doesn't replace it.
And there's this brilliant subtlety to the design too. The band is intentionally fitted so that the drum's downward rotation under load actually drags the band tighter. We call this a self-energizing system. It essentially uses the energy of the falling load to clamp itself down, amplifying the driller's hand force by hundreds of times in the direction that matters most. If the drum turned the other way, that exact same pull would barely grip at all. All right, section 4, silent system killers, failures in the physics. Now, here's the danger of relying on such elegant mathematics. Because this whole system runs on exponential physics, microscopic errors in maintenance can result in massive, catastrophic failures. Small changes don't just reduce your braking power by a few percent, they can literally have it instantly.
Let's test yourself again, this time with a maintenance scenario. The flexible steel band is lined with consumable friction blocks. If you inspect it and see you only have 2 worn blocks on the whole band, why is it a terrible idea to just swap out those 2 bad ones and leave the rest alone?
Well, it's because thickness sets the contact. If you mix thick new blocks with thin old ones, only a tiny fraction of the surface, literally just those new thicker blocks, actually makes contact with the drum. Suddenly, those 2 little blocks are taking the entire 150-ton heat load all by themselves. They'll instantly overheat, glaze over, and fail. Uniform contact is the whole point of a band brake, which is exactly why they are always replaced as complete sets. No shortcuts.
And that brings us directly to the 3 silent killers of this mega machine. First up is glazing, which is where the overheated friction lining turns glassy and slick, completely losing its grip. Second is heat checking. That's when extreme thermal cycling causes the steel flange itself to crack in a spiderweb pattern. And third is contamination, where outside fluids somehow get between the band and the drum.
I really want to emphasize that last point. On a rig floor, contamination is not just a minor housekeeping issue. It is a total control failure. Seriously, a single drop of oil or water from a leaking seal, landing on that exponential friction curve, can cut the braking power so drastically that the load just keeps dropping, even with the driller's lever pulled back to the absolute max.
So I'm going to leave you with this provocative thought to carry with you today. On a rig where 150 tons hang suspended in the air, your survival depends entirely on the physics of friction. What happens the moment you overwork the system and that friction silently fades away right when you need it most? Exponential physics amplifies your strength? Absolutely, but it will also ruthlessly amplify your mistakes. Thanks for joining me on this explainer, and keep questioning how the world around you actually works.